This is my mass on a spring, and we're going to solve its motion in a similar way we did the trajectory. But first I want to point out that this mass is in a special situation. It's at a point of stable equilibrium. What that means is that the net force on the mass is 0. So right now the mass isn't moving, and the force is 0 because gravity is pulling it down and the spring is pulling it up. So one property of stable equilibrium, the total force is 0. Another property is if you move away from the point of stable equilibrium, the forces push it back. So if I pull it down, now the spring force is increased, the gravity is the same, so it pulls up. If I push it up from its point of stable equilibrium, spring force goes down, or it decreases, gravity is the same, so gravity pulls it down. So what we want to figure out is what kind of motion do you get? Now, I'm going to kind of give the answer away because we're working on simple harmonic motion. So let's see what that means. So first, let me draw the system. So we have the spring connected to something solid and heavy like a wall, and here's the spring connected to the mass. You may recall from mechanics that we describe a spring with a spring constant K in newtons per meter. That's how you get the force in newtons from the deflection in meters. And the mass, of course, is in kilograms. But it's important to keep up with our coordinate system. So here is the x-axis, and we want to put the origin in the right place. So I'm doing this sideways to avoid gravity. We don't have to think about what a constant force would do for now. And we also want to think the spring has a natural length, right? It wants to be a certain length, and it applies a force when you deflect it from that length. So right now we'll say at its natural length, the mass ends up at the origin. That just makes the problem simpler. Okay, so we have our physical situation. Let's apply Newton's second law. So the sum of the forces in the x is the mass times the acceleration in the x. So the force you feel is the force from the spring, and you may recall from mechanics that that is defined by Hooke's law. Springs give a force minus kx, where k is their spring constant and x is their deflection from their natural length. And the minus is there because you can kind of see if I move this mass to positive x, the force is negative, is back. If I move the mass to negative x, the force is forward, positive. That's why the negative sign is what tells you that a spring always pushes back. So we have minus kx equals m, and then I'm going to give you a new notation. I'm going to call this x double dot. Okay? So recall that x meant x as a function of time. That's what it always means in kinematics. And we're going to say something called x dot basically is just another way to write dx dt. Just to have to avoid writing dx dt and d2x dt2 over and over again, we use this convenient dots. d2x dt2. See how hard it was to write at the bottom of the board. So that's all that means, same as last time. So now we have our equation of motion. Minus kx equals mx double dot. So if you're new to differential equations, here's your second one. So let's solve it. We could attempt to solve it by integration. So the right side would become what? mx dot. And the left side would become what? Minus 1/2 kx squared, right? No, not right. No, 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 no. I should not have written that on the internet. That should never happen, okay? So one important thing in these problems is to keep up with your functions and your independent variables and your dependent variables. So remember, x is a function of time. To integrate an equation of motion like this, we integrate with respect to time. So we did the right side right. Integral of that with respect to time is m times x dot. But this side, we didn't integrate it with respect to x. We need to integrate with respect to time, right? If we integrate with this with respect to x, that would be minus 1/2 kx squared. We need to integrate with respect to time. So we need the integral of the x function with respect to time. But we don't know what the x function is. That's what we're looking for. So right off the bat, your second differential equation is tricky and you can't even solve it. Well, let's see if we can figure out what to do.